Okay, so this is the fourth problem in the series of optimization problems we've been looking at. And in this question, we see that a man is standing at point A on the bank of a river, and he wants to get across to his girlfriend who's 8 kilometers downstream on the opposite side. So he needs to get from point A to point B some way, and he's got a couple of options here. He could swim straight from A over to B. That would be the shortest distance. Or he could swim the shortest amount of time in the water over to part C, and then run all the way down to point B. Or he could do somewhere in the middle, where he goes from A to some distance in the middle, partway between C and B, and then run the rest of the way. And the question is, which is the best way that he should do this if he wants to get there as quickly as possible? In other words, if he wants to minimize the amount of time that he's in the water. So the first thing we should probably do here is try and understand a little bit about the nature of this question. Under what circumstances would it make sense for the guy to swim from A over to B? Well, certainly if he can swim faster than he can run, then he would go from A to B. In fact, even if he could swim at the same speed as he could run, he would go from A to B because that would be the shortest distance. Now, imagine that he can run a little bit faster than he can swim, but not too much. Then it's not going to make some sense for him to go all the way across the sea and then run all this distance, because it's quite a bit shorter if he goes straight from A to B. But if he can run faster, he probably wants to spend a little bit less time in the water, so maybe instead of landing at B, he lands over here somewhere. Now imagine he can run a little bit faster. Well, then he moves a little further this way. Imagine he's got a bicycle waiting for him on this side and he can ride his bicycle. Well then, again, it's going to be a little bit this way. And as the difference between his speed in the water and his speed on land increases, as the difference in those speeds gets bigger, he gets closer and closer to point C. The question is, when would he actually go straight to point C? And it seems a little counterintuitive, but he'll never get to point C. That would never be the strategy. Even if he's got a Ferrari waiting for him on the other side of the river, and he can drive 250 kilometers an hour from wherever he lands down to point B, he's still not going to go straight across to C, because it's going to take a little bit longer because he's going a greater distance. So the answer to the question, first of all, is that he's going to go to some point D. Now the question is, where is point D? And that's what we're really asked to find out here. So this is an optimization problem. We're trying to minimize the amount of time that he spends. So let's start there. And we're going to say what we want to do here is minimize his time, and then we need an equation for time. Time equals. And it's difficult to see what equation we might use in this one. But like I said before, if you don't know what equation to use, any equation is better than no equation. So we can say, well, the time he takes would be the sum of the time he spends swimming plus the time he spends running. That seems reasonable. And now the only problem we've got is that this formula, this equation, is in terms of two unknowns. Okay, TS is a variable and TR is a variable, and we need it to be in terms of one unknown. So now we got to go back to the diagram and think a little bit about what's going on here. Well, first of all, I could convert these. I can see that in my diagram I've got distances. And so I think I want to involve distances. And I know that we've got this formula which says that speed is equal to distance over time, which implies that time is equal to distance over speed. And so I could rewrite my equation a little bit better, and I could say that his total time would be his distance swimming divided by his speed swimming, and his speed swimming we know. His speed swimming is 6. Plus his distance running divided by his speed running, and we know that his speed running is 8. So that's a little better, not much. We've still got two unknowns, but at least they're better unknowns. They're unknowns that seem to somehow relate to the diagram we've got up here. So now what we need to do is figure out how we're going to get this in terms of a single unknown. And probably the best thing to start with is to actually put these two variables that we've got on our diagram. So the distance he is swimming is that distance, and the distance that he's running is that distance, assuming that he lands at D. What we want to do is we want to make use of the fact that we know that this distance from C to D is 8, and this distance across the river is 3. So the first thing I notice is that if that's a 3 and that's a ds, that looks very much like something Pythagorean. And so what we might want to do is say, well, let's consider the third side of this triangle over to here. And let's call this, I don't know, x. So now I could relate the distance swimming to x. The distance swimming would be the square root of 3 squared plus x squared. So this now becomes the square root of 3 squared plus x squared over 6. The problem is now I've got a new variable x, and I've got my original variable dr, and so I've still got two unknowns. But now we can see what we're going to do up here, I think. Because if this distance from c to d is x, and the distance from c to b is 8, then clearly this distance must be 8 minus x. The distance running is 8 minus x. And so I can now put that into my equation. And my equation finally becomes 8 minus x over 6. And now I have an equation for time in terms of a single unknown. Now I'm going to need to do the domain, the physical domain of this problem. So I want the domain of time. And my variable is going to be x. And the question I have to ask is, what is x allowed to be? Well, clearly x couldn't be negative. I mean, I suppose it could be, but it wouldn't make any sense in the problem, would it? If x was negative, then the guy would be swimming to the left of c, and that's clearly not going to be the shortest amount of time. So x has to be bigger than 0. And likewise, there's no way he's going to land on the far side of b. For him landing out here would just not make any sense in the problem because he's trying to get there as fast as possible. So x has got to be less than 8. Now, it could be equal to 8, but remember we said the only way it could be equal to 8 is if his speed swimming was equal to his speed running, and we know that it's not. So it's going to be less than 8. So that's my domain. Now from here, I can go on and I can start to solve the problem just like every other optimization problem that we've ever done. So the next thing we're going to need is the derivative. So let me just rewrite my equation. The equation I had was t equals the square root of 9 plus x squared over 6 plus 8 minus x over 8. And I want to take the derivative of that. So I want the derivative of t with respect to x. So working this out, well, this is a 1 over 2 root box kind of thing. So 1 over 2 is going to make that 6 a 1/12. So I'm going to have 1 over 12 times the square root of 9 plus x squared. There's my 1 over 2 root box. And then I'm going to need a d box, and that's going to be a 2x coming out of there. And here, well, I think I would choose to think about this 8 minus x over 8. I would think of that as being 1 minus x over 8. 1 minus 1/8 x. That's much easier to differentiate. The derivative of 1, of course, is 0. The derivative of minus 1/8 x is just minus 1/8. So this is going to switch sign here, and we're going to have minus 1 over 8. Now I've got my derivative. Now I need to solve that for equaling 0, and I need to find out where that doesn't exist. So I look first at where it's not going to exist. The only way that this whole thing is not going to exist is if I got a division by 0 in my denominator. The only way that happens is if 9 plus x squared is 0, and 9 plus x squared is always going to be greater than 0. Likewise, you might think that I could have a negative even root here, but again, the 9 plus x squared, the smallest that could ever be is 9. And so we don't have any division by zeros, we don't have any negative even roots, and so therefore I can say that t prime exists for all values of x in my domain. Now I can look at where t prime equals 0. And t prime is going to equal 0 when, well, I can see up here I've got a 2 and a 12, so that'll reduce down a little bit. So I'm going to be left with x over 6 root 9 plus x squared. And I think of taking the minus 8 to the other side because it's equal to 0. So that's going to now equal 1 over 8. So if I cross multiply here, I'm going to get 8x equals 6 times the square root of 9 plus x squared. I can divide both of these by 2, and that's going to make this a 3. That's going to make this a 4. And now to deal with the square roots, I'm going to square both sides of this equation. So I get 4x quantity squared is 16x squared. And when I square the right side, the 3 becomes a 9. And the 9 plus x squared loses its square root. And now this is going to be easy to solve. 16x squared equals 81 plus 9x squared. So 7x squared equals 81. So x squared equals 81 over 7, which gives me x equals plus or minus, the square root of 81 is 9 over the square root of 7. But we already said that my domain has to be greater than 0. So I know that that is extraneous. And so my only root is x equals 9 over the square root of 7 kilometers. That's my only critical value. And so now I just need to test that critical value. So I set up my labeled sign chart. I'm going to have one vertical bar and, as always, two horizontal bars. My vertical bar is going to be x equals 9 over the square root of 7. And here I'm going to have t prime and t. To the left of 9 over root 7, I could take something like 1, and I could plug that into my equation. And I know that that if I plug a 1 in for t prime, I get a negative here, which tells me that the time is decreasing. And likewise, to the right, although I'm only supposed to go as far as 8, nothing's going to change if I go farther. But even if I plug in 8, I can see clearly that this is positive. This is increasing. I know that my derivative was 0 at 9 over root 7. And so this information tells me that this is a local minimum. And because it's decreasing all the way into 9 over root 7 and increasing all the way from 9 over root 7 to 8, I can see that not only is this a local minimum, it's an absolute minimum, and I can justify it that way. So I say, therefore, t has an absolute minimum when x equals 9 over radical 7, because, and if I look up here at my chart, I can see the reason for this is because t prime is less than 0 for all values of x between 0 and my critical value at 9 over radical 7. And likewise, t prime is greater than 0, which means that t is increasing for all values of x from my critical value at 9 over radical 7 to my endpoint at 8. So, in conclusion, the man should swim to a point 9 over radical 7 kilometers downstream from point C. And that will get him there the fastest. I hope this makes sense. If you have any questions, feel free to send me an email or come see me in class, and we'll go over it together.